Imagine a construction site where you have 100 workers but only 10 trucks to move materials. That is the fundamental architecture of virtual threads in Java. You create thousands of lightweight tasks, but they need physical trucks, called carrier threads, to actually do the work. In the early versions of this technology, there was a fundamental flaw. If a worker got stuck waiting for a material, the truck they were riding in would sit idle. This is known as the pinning problem. The carrier thread becomes pinned to the virtual thread, unable to pick up other work. It is like a delivery driver stuck in a traffic jam who cannot drop off the next package until the current one is resolved. Here is the thing that makes this difficult to debug. The symptoms often look like a standard deadlock, but the root cause is different. In a traditional deadlock, two threads wait for each other. With pinning, a single thread waits for a resource while holding the only carrier available. This effectively kills scalability. You might have thousands of virtual threads, but if they are all pinning to a few carriers, you are back to square one. The performance bottleneck is hidden in the synchronization primitives. Specifically, when a virtual thread enters a synchronized block, it binds to the carrier for the duration of that block. If that block involves a blocking operation like a database call, the carrier is held hostage. To understand the fix, we need to look at the investigation process. We start by creating synthetic pinning triggers. These are controlled scenarios where we force a virtual thread to enter a synchronized block and then block. We trace the carrier thread state. In Java 21 and earlier, the carrier thread enters a waiting state. It cannot be reused. It sits there until the virtual thread wakes up. This is the behavior we are trying to eliminate. Now, consider the scenario in Java 24. This version introduces a transformative fix through a specific enhancement known as JEP 491. This update changes the contract between the virtual thread and the carrier. Previously, the synchronization monitor was a hard lock on the carrier. Now, the system allows the virtual thread to suspend while holding the monitor, but the carrier is released to serve other virtual threads. This means the synchronized block executes without pinning. The carrier thread is free to move on to the next task. This distinction is critical for forensic debugging. When you are tracing a performance issue, you need to know if you are dealing with a genuine deadlock or a pinning artifact. In a genuine deadlock, the threads are mutually blocked. In a pinning scenario, the thread is waiting, but the resource it needs is available, yet the carrier is busy. By using the new instrumentation tools available in Java 24, you can observe the carrier thread life cycles more granularly. You will see that the carrier does not stay in the pinned state during the wait. It detaches, allowing the virtual thread to be suspended on the heap while the carrier returns to the pool. This shift signals a paradigm change in how we write concurrent code. For years, developers avoided synchronized blocks in favor of lock-free algorithms or reactive patterns because they feared the pinning overhead. Now, the JVM handles the suspension and resumption transparently. This reduces the need for explicit lock-free patterns for simple synchronization. The complexity moves from the application layer to the runtime layer. Let us walk through a comparison. Imagine a factory assembly line. In the old model, a worker stands at a station. If the machine jams, the worker stops and the conveyor belt stops moving. No one else can use that station. In the new model, the worker steps away when the machine jams, but the station remains reserved for them. The conveyor belt keeps moving because the worker is no longer physically blocking the line. The reservation is logical, not physical. This is what the Java 24 update achieves. It decouples the logical lock from the physical thread binding. Community validation supports this shift. Examples from major frameworks like Spring Boot show that applications previously hindered by monitor contention are now seeing significant performance improvements. The fix resolves critical bottlenecks in real-world applications. It allows legacy synchronized code to run efficiently in a virtual thread environment without the architectural overhead of carrier thread management. However, this does not mean all synchronization problems disappear. You still need to design for concurrency. But the fear of the pinning problem is no longer a reason to avoid standard monitors. The evolution from pinning to non-pinning synchronized operations simplifies the mental model for developers. You can focus on the logic of the synchronization rather than the mechanics of the thread carrier. In the future, Java development will likely see a reduction in the complexity of concurrency patterns. As the JVM handles virtual thread suspension and resumption transparently during synchronized operations, the burden on the developer lightens. This is not just a performance tweak, it is a fundamental shift in how the platform supports concurrency. It allows virtual threads to fully leverage hardware concurrency without the previous limitations. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.